Mars has always haunted us. It's not just a neighbor in the sky, it's the planet that most resembles our own. Rocky, familiar, touched by winds and seasons. Once it had water, possibly even oceans, and maybe, just maybe, life. We've searched for that life in soil samples and in craters, in ancient riverbeds and dry lake basins. But what if the most telling clue isn't in the ground, but in the air? A molecule, odorless, invisible, ephemeral, methane. On Earth, it's common, a byproduct of both life and geology. But on Mars, its presence is unsettling and full of meaning, because it shouldn't be there, not in a world so cold, so still. And yet it is. Methane has been detected on Mars, repeatedly and erratically. Sometimes it surges, sometimes it fades. Sometimes it's measured by rovers on the ground, other times by orbiters in space, and often by neither. What's causing this elusive gas to appear and vanish? And more importantly, is it a geological whisper or the breath of something alive? To understand why Martian methane matters, we need to understand methane itself. On Earth, it's produced in abundance by life, by industry, and by natural processes. Wetlands, rice fields, landfills, livestock, they all produce methane. Deep underground, geological forces do too, in tectonic fractures and volcanic vents. But methane is fragile. In Earth's atmosphere, it breaks down over time, oxidized by sunlight and chemical reactions. Its lifespan here is about 10 to 12 years. On Mars, the rules should be even stricter. Its thin atmosphere and lack of oxygen mean methane should linger even longer, perhaps centuries. Yet what we see there is the opposite. When it appears, it doesn't last. Sometimes it vanishes within months. Other times, it can't be seen from orbit at all, even after a spike was measured at ground level. This suggests something strange is happening. Either methane is being produced at unpredictable intervals, or something is destroying it faster than we ever thought possible. Either answer implies something unknown is at work. The story began in 2003. Astronomers using Earth-based telescopes noticed something odd in the spectral data, a subtle but distinct signal of methane in the Martian atmosphere. It wasn't much, but it was real. The following year, ESA's Mars Express orbiter confirmed it. Methane wasn't just present, it was concentrated in certain regions. This wasn't random. Something, or some process, was producing it. Then came Curiosity. NASA's rover, which landed in Gale Crater in 2012, wasn't just built to analyze rocks. It could sample air too. In 2013, it recorded a small but clear burst of methane, a sharp spike followed by a return to baseline. Later spikes would be even more dramatic. In 2019, Curiosity measured a sudden surge to 21 parts per billion, the highest ever observed on Mars. But what truly deepened the mystery was this. Orbiters flying overhead saw nothing. This raised a critical question. Was methane only present at ground level? Or was something interfering with our ability to see it from space? What followed was more than a debate. It was the start of a scientific reckoning. One of the leading theories doesn't involve life at all. It starts with rock, specifically a process called serpentinization. On Earth, when water seeps into cracks in ultramafic rocks rich in iron and magnesium, like olivine, and heats up, it can trigger chemical reactions that produce hydrogen and, in turn, methane. It's a slow, steady process, one that requires no organisms at all. We know Mars has olivine. We know it once had liquid water, and some evidence suggests that briny subsurface water might still exist today, locked beneath permafrost or trapped in deep aquifers. So could this be the answer? If these slow chemical reactions are occurring beneath Mars's surface, methane could be leaking up through ancient fractures, released by shifts in pressure, seasonal cycles, or even meteor impacts. But there's a problem. Mars is geologically quiet. Its volcanoes are extinct. There are no confirmed tectonics. Serpentinization could be happening, yes, but it wouldn't explain methane spikes that appear suddenly, then vanish just as fast. The behavior of the gas doesn't align with slow geology. It suggests something more active, more localized, more alive. Now we enter dangerous territory, because when we talk about methane and life on Mars, we must walk the line between science and hope. But the evidence, however circumstantial, can't be ignored. Here on Earth, about 90% of methane is biological in origin. Produced by microbes called methanogens, these tiny organisms thrive in oxygen-free environments, from ocean floors to ice-covered lakes to the stomachs of animals. Methanogens don't need much, just hydrogen, carbon dioxide, and a place to live. If similar organisms ever evolved on Mars, perhaps billions of years ago when the planet was wetter and warmer, they could still survive today. Deep underground, beneath radiation and temperature extremes, shielded by rock, fed by underground water and minerals, they could persist. Dormant, maybe, sporadic, but real. And when conditions change, when a pocket of gas expands, when a fracture opens, they could release a puff of methane into the Martian air. To us, it would be a whisper, a trace, but to science, it would be a revelation. But the mystery isn't just about where methane comes from. It's also about where it goes. Methane shouldn't disappear from Mars's atmosphere so quickly. According to known chemistry, it should linger for centuries. And yet, it doesn't. We've seen plumes vanish in months, sometimes weeks. So something on Mars is destroying it. Some scientists point to perchlorates, chlorine-rich chemicals found in the Martian soil. They're highly reactive, and when energized by sunlight or dust storms, they could break methane apart. Others suspect airborne dust, charged by electrostatic forces, could play a role in rapid methane degradation. Some propose exotic photochemistry, unknown reactions triggered by ultraviolet light in the thin Martian air. But so far, none of these processes fully explain the rates we've observed. It's possible we're seeing something completely new, a Martian chemistry we don't yet understand. And that might be the biggest clue of all. The hunt continues, more precise, more determined than ever. ESA's Trace Gas Orbiter has been mapping methane from orbit, seeking patterns. NASA's Curiosity keeps monitoring the atmosphere from Gale Crater, gathering seasonal data. Future missions will go deeper. The Rosalind Franklin rover, when launched, will drill up to 2 meters below the surface. The first mission equipped to truly probe the Martian subsurface, where methane might be born or exhaled. Even more ambitious plans are in development. Sample return missions, spectrometers that can analyze isotopic ratios, signatures that could distinguish between life and non-life. And one day, perhaps, a human being will stand on the red sands of Mars, hold a vial of gas, and know exactly where it came from. Methane is just a molecule, but in the vacuum of space, in the barren air of another planet, that molecule speaks volumes. It speaks of chemistry we don't understand, of geology we haven't mapped, of biology we haven't discovered yet. It hints at Mars as a living system, not in the way Earth is alive, but in its own quiet rhythm. A planet that breathes, even if just once in a while. And it invites us to imagine a future, not just of rovers and drills and labs, but of contact. Not with civilizations, not with science fiction, but with a truth older than our species. That life finds a way. And perhaps, in the shadows beneath the red dust, it already has.